Draw the inference line. For bending moment at point B. Okay, just give it a try, then I will solve it. Follow the Mueller steps. Okay. What is the first step of the Mueller? Yes.
Replace it with an equivalent support.
Replacing is comes after that. First step is remove of the constraint. The constraint is moment at point B. And then, as Braden said, replace it with a proper hinge or support. So if I remove bending moment at point B, you already know that the force system is like this. We have bending moment, we have shear force, and we have normal force. You always have this force system, always, according to this sign convention. So we remove the bending moment. So what remains is the shear force and the normal force. So what is the proper replacement here? Selena. What joint should I put here? Is it shear hinge? Is it pin or is it free or what? Pin?
Yes.
Okay, yes, because it doesn't carry bending moment, so I just put a pin here. Proper joint. So the next step is applying a unit displacement or rotation. So which one? Is it displacement or rotation?
Would it be rotation since you're solving for a moment?
Yes, it is rotation because we solve for moment. And it must follow this sign convention for the rotation. So it means you put your thumb here and you rotate in this manner, based on this direction. So your structure will deform in this way. After you rotate. So the angle here is alpha. We don't know this angle. The angle here is beta. According to geometry, you know that this angle is alpha and this angle is beta. The question is, how much is the amount of rotation when you apply the rotation? Simon, how much is the amount of rotation? It must be unit, right? Unit rotation. So how to apply a unit rotation here? This is the interpretation of Mueller principle. So the way we interpret it is that the slope must be unit. So it means the slope at this side and this side together must be unit. It means tangent of alpha plus tangent of beta together is equal to 1. Unit slope. It means the slope at this side and this side together. So don't forget this when it comes to bending moment internally. And then from here, the amount that, let's say this amount is delta. From here to here. This is delta. We are looking for the amount of delta because when you draw your yellow color inference line, you must have the dimensions as well. So using geometry, we expand this formula. In the first triangle, which is a right triangle, tangent of alpha is opposite divided by adjacent. And we assume that this is A and this is B. So in the original question, we assume this is A and this is B. A and B are just parameters. So tangent of alpha is delta divided by A. Tangent of beta is delta divided by B. Any questions so far? I'm going to move a bit faster, but unless you ask questions. If you don't ask questions, it means you understand. Okay, so from here we solve this equation based on delta. So delta is AB divided by A plus B. And then A plus B is the length of your beam, which is L. The span of your beam. And then we are done. So it is better to redraw it in the exam. If you want to draw the inference line, this is point A, point C, point B. This is the inference line, and delta here, delta is AB divided by L. That's it. Next question. And these are important and typical questions, so you should review them for the exam. I carefully selected this question. Next question is asking inference line for bending moment internally again, so it's kind of practice of this. We have a beam, the support is fixed support, internal pin sitting on a roller. We have a shear hinge, and at the end we have a roller. A, B, B, C, D, E, F. The question is asking for inference line for moment at point B. We can give it a try, then I will solve it. Okay, the first step is the remove of the constraint, which is bending moment at point B. So similar to what we have done here, we remove it and we replace it with a proper internal joint. Again, similar to what we have discussed here, and Selena already answered. It means we have to put an internal pin at point B. This is the first step. The second step is applying a unit rotation, as Adrian said, because we are solving for bending moment, so we have to apply a unit rotation. So how do you apply a unit rotation at two sides of hinge B or pin B? Remember, yes.
The left side is going to be
Stable.
Yeah.
Mhm. So the left side is stable, so it doesn't move. So the only choice is just applying a unit slope at the right side of the pin B. How would it deform? We call it deflection shape. This is the one that you have to imagine in your mind and then draw it, the deflection shape. So, okay, because I have to follow this sign convention, it means the segment from B to C will rotate in this way. And this angle is 45 because the slope must be unit. The problem is how the rest of the structure will be deflected. So you grab point C and pull it downward. Of course, CDE is a rigid continuous element. It's a single element. So it moves with all its components. So it has to rotate in this way. There is no other way. How would you draw the rest of the structure? EF. Why? There was a principle, two sides of shear hinge must remain parallel. So if you want to have EF parallel to this line, this is the only way. They have to be parallel, always. And the rest is not difficult, you just find the, based on the angles that you have. This angle is 45, so this is L over 2, this is L over 2. This angle, so this one is L. And then from the compatibility equation, you just find the other values. So this one, my drawing is not to the scale. This is L over 2, L over 2. This angle is equal to this angle, equal to this angle. They are parallel. But my drawing is not to the scale. Any question? Next question is, I'm sure you can find these values based on the geometry. It's not difficult. The most difficult part of it is deflection shape. Next question is asking to draw the inference line for, again, for internal moment at a point. We have pin support, roller, internal pin, roller, shear hinge, the question is asking for inference line of bending moment at point B. The dimensions are all equal. L, 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 L. So give it a try, then I will solve it. And it would be nicer if I could ask one of you to come to the board voluntarily, but basically we don't have time for that. So we have to cover all of the articles. That's why I just solve it by myself. Okay. The first step is the remove of the constraint. So constraint is bending moment at point D. How do you remove it? Because point D already has a pin. So how are you going to replace it with a pin again? Race, what do you think?
Change it from a roller to just a bin.
No. I will draw this beam with blue color, and I just want to give it a little dimension because it's a beam. Okay, this is your beam. Now, can I put a pin here?
Yeah.
Can? Yes. The pin here is for the support. It has nothing to do with the internal moments of the beam. So when we cut this pin here, so you, as usual, you can place an internal pin here, and it has nothing to do with the support. Basically, you're breaking the beam and placing a pin inside the beam. It doesn't matter if your beam is sitting on a pin already. And basically, you can say, okay, so there are two pins together, and two pieces of beam are separated, so why not? You just combine them together. So basically, you would have one pin which is serving for the beam internally, and it is also serving for the support. That is how we replace. Then the next step is applying a unit rotation at point D. Okay. Try to challenge your mind because these are the problems in your exam. So I want you to do it maybe wrongly and then I will solve. So I give you 30 seconds. Draw the deflection shape and then I will solve it. Okay, tell me what do you think? We start from the left side, from AB. Do you think that AB will move? No.
It's stable.
It is stable because it is fixed between A and B. So it doesn't move. Stable. What about BC? Remember, ABC is a single rigid continuous element. So if A and B are fixed, C is attached to them. So ABC is totally stable. Okay, and basically we are going to apply a unit displacement or rotation for point D. What about CD? Is CD a single rigid element?
Yes.
Yes.
Yeah.
It is already connected to point C. Remember, point C doesn't move. So point C is there, fixed. Now you want to lift up point D. Is it possible? I draw it and then you tell me if it is correct or not. One of the choices is rotating CD in this way. Is it possible?
No.
Why?
It's got a counter force.
Yeah, because point C doesn't move. Point C is fixed. So it's not possible. What about this one? No, because point C. So what is the choice? CD is also stable. It doesn't move. Because point C is fixed. Point D is also fixed in place. Of course, CD can rotate about point D, but point C doesn't allow it. Okay, so CD is also stable. These are the challenging part. CD is also stable. Unless you tell me there is a way for that. Clement, is there any way CD rotates when you know that point C is fixed in place?
Would C still be able to rotate up since?
No, because ABC is already attached to A and B, so it cannot rotate up.
It's saying rotate CD around C.
It's like, if B is only upward force, so there's nothing pushing it down.
I mean, you tell me how do you want to rotate? I draw it.
So going up and then C.
Okay, which one goes up? Which point?
I'll just start with C.
Which one?
Start from D, go up.
Okay, go up. And then what about C?
Sorry, I mean, D is the same point and then C goes up. So
No, C cannot move. C is fixed in place because it is attached to A, B, C. How C cannot move up?
why can't C move up?
Because this is a single rigid element attached to A and B. How do you lift it up?
If B isn't pinned to the ground, that still count as.
It's like this. So I draw it here. This is A. This is B. The pin is in outside. So how do you lift point C? How?
Why wouldn't I be able to do that?
No.
B up.
What? B up? No, B is already attached to this pin, and this pin is attached to the ground. How do you want to lift the ground up?
Oh, okay,
Right?
I got it, yeah.
Yeah. So you need to practice this kind of thing. That's it. Okay, so basically CD is fixed. So Clement tried his best to rotate it, but he couldn't. Okay, so now you have to apply a unit slope at point D. So you cannot apply it at the left side. So you have to apply the entire unit slope at the right side. Okay, at the right side. And you need to follow this sum convention. Okay, I apply a unit displacement. How much is this angle? 45. So when this is 45, then of course you know the dimension, whatever, is L, so this is L. So what about EF?
Has to be parallel.
Mm-hmm. Yes. Okay, parallel. Done. And then you know this is L, so this one is L. You know this one is parallel, so this is 45, etc. Okay. Next question. Is there any question?
So let's say if B was an internal roller, what?
Then
C-
then that would be another question with another challenge. So I will try to answer your question, but if you want to change anything, then you can create a say again.
So I'm just trying to understand, like, if B was an internal roller instead of it being on the outside, would
So-
that then change just AB to be stable? And
So
then
you
C-
say if the pin is inside?
Yes.
Okay, let's say if A. Okay. Then that's another, yes, then C, then BC can rotate.
Okay, that was my question.
Then why? Because ABC will not be a single rigid element. Now you have two different elements. Yes. Okay, next. I try to cover different types of problems, as many problems as possible. The next question said, internal moment for, so we have a fixed support here, A. we have internal hinge, we have a pin support, but pin is not inside the beam. So A, B, C, D, E. The question is asking for inference line for M at point C. That's it. Inference line for moment at point C. Basically, this is similar to the question from Adrian. He just asked. Similar to that. So let's do it. We are going to place so we place a pin inside the beam. But you know what was the original question, right? Pin originally was not inside the beam. And then you have to apply a unit slope at point C. What about element AB? AB is stable because it's a cantilever. So AB doesn't move.
BC is also stable.
You cannot, point C doesn't move up and down because it is attached to the support, but it can rotate. So,
But since a sliding hinge doesn't allow for rotation, would BC still be rigid?
you're talking about BC, right? So now, yes, that's a question. No, BC is not rigid because BC is a separate element. BC can rotate about point C. So we cannot say it is stable, but if you want to rotate BC, it will have different slope at two sides of shear hinge. Remember, two sides of shear hinge must remain parallel. So if this is the direction of AB, this has to be the direction of BC. They must be parallel. So we have no choice other than just drawing this line here, because they must be parallel. Is there any other way, Clement, for BC? BC must be parallel to AB.
Would the moment transfer like you did with the other ones before, or would it?
Yeah. So we will look into CD later. But now we are talking about BC. BC must remain horizontal because two sides of the shear hinge must be parallel.
Oh,
So there is no way unless you tell me.
okay, no, I get it.
So BC supposed to rotate, but it cannot because it must remain parallel. Okay, so now we go to CD. 45, and then of course DE can rotate because we already have a pin at point D. That's it. 45, and then this is L because this is L. Next question. Yes?
So if D, in the last question, if DE is able to kind of do it, why can't we do it with BC on that one?
Because the other side is rigid, and you have to have
Mhm.
you have to have parallel slopes across a shear hinge.
Because AB is stable here, but EF doesn't need to be stable here.
That's why.
Yeah. So if you change a little, the entire solution will be different. You know, you just make a change in the question, everything is different. Next question is inference line for internal moment again. So we have a fixed support, we have a shear hinge. Let me see. We have C support here. Internal pin at point D. Shear hinge at the end. Of course, the dimensions are L, 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 L. The question is asking for reference line for MB. Try it. Okay, Braden, you are good at it. What is the replacement joint at point B?
I'm stuck between either a pin or
No, you already answered this question, previous question. You stuck between what? Pin and?
free. Like,
It is about MB. So why do you want to put pin? Because it is
I was
MB.
to say because the shear hinge doesn't allow for rotational moment.
Yes. So basically you have freedom for rotation, you have freedom for shear. So the only thing remains is,
Normal.
yeah, so you always deal, conceptually, you always deal with this. I'm sorry I cannot give you more time to challenge your mind because we have to cover. You always have this force system. Always. And then you have to remove something. So I'm going to remove, as Braden said, moment, remove the constraint because it's about bending moment. And we already don't have the shear because it's a shear hinge. So the only thing remains is the horizontal one. In most cases, maybe 90%, 99%, we don't care about the horizontal one because we don't have horizontal force for the beam. So as he said, it's free. If you want to remove it and redraw it, so basically when it comes to point B, it's free. So this is after remove of the constraint. Next step, apply a unit slope in this direction. Again, Braden is good. What about AD?
AB's rigid. No move.
It is stable. It is stable. Yeah? Okay. Now, Tommy, what would you do with BC? Are BC and CD separate elements or the same single element? BCD. Simon. BCD is a single element or what? Yeah, it's one element. So it is one element, so it cannot break at point C. So whatever you do with BC basically must go through CD because it's a single element. So you are going to rotate it. Okay, let's rotate. It's a single element. And this angle is 45. Of course, this angle is 45. What about DE?
Stable. Or,
No.
uh,
You wanted to say something, not stable, but
horizontal line.
I think Adrian wanted to say, yes, horizontal. Because it can move horizontally, right? Yes, that's it. It's a shear hinge, so it can easily move. Yeah, that's it. And the dimension, of course, this is L. Next question. We have a pin here,
It's like one of those two-sided screws. The nuts, where the rest is code.
shear hinge,
Or it's just two flat surfaces.
pin support at point C, another shear hinge, pin support, another pin support. Inference line for ME.
Are those all external to the beam? Except
They
for
are
that?
all external, so it means, yes, they are all external pins at E and F. They are not internal. They are external.
Oh, the beam rests on that?
Yes, the beam is resting on E and F. All the pins are external.
Except A?
Sorry?
Except A or including A?
No, A is just a support, of course, it's here.
Okay, okay.
So if I want to draw it, this is the beam. Yeah. So the pins are outside the beam. For this one, I give you 30 seconds. Okay, what is the first step? You should always draw the force system. This is ME, so this is the one that you are going to remove, and the direction of your sun convention. So you need to put a pin, you place a pin at point E. So similar to the previous question, you place the pin at point E inside your beam. Okay. Any question, Clement? Do you agree with that? Okay. Next step, apply this unit slope. I don't know. What is your, I forgot your name. So, yes. How do you think about EF? Does it move? Is it stable or what?
Yeah, I don't think it's stable.
It is stable because point F doesn't move upward and downward. Point E doesn't move upward and downward. Do you? So what to do with EF? You grab it and then you try to rotate it. It's not possible. So it is stable. And what about DE?
Fixed. It has to slope.
Okay.
Like, yeah, like that.
What about CD?
C is fixed.
Up.
It's going to be rotated.
Yes, Simon said up. But what about BC? BC is attached to CD, it is a single element, right? So if you rotate CD, then BC is attached to it because it's a single element. And you know the reason, because two sides of shear hinge must be parallel. And what about AB?
Parallel.
Parallel to.
Yes, parallel, yeah. That's it. And so this angle is how much?
45.
45. This is parallel, 45, 45, 45. I don't show the dimensions, but in the exam you need to show the dimensions. So it's easy. When this is L, 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 you know how to find. Okay. Next question. We have a pin support, another pin support, shear hinge, and pin support at A, B, C, D. And then the last part of the beam is just cantilever. A, B, C, D. So pins are outside. So this is your beam. The question asks for bending moment for MB. In first line for MB. Just give it a try, then I will solve it. Oh, sorry. This is MC. This is MC. Just change. MC. In first line for bending moment at point C, because we already practiced a lot for internal moment. The first step for bending moment at point C, we already have a shear hinge at point C. So always go for this way. Force system. So you are going to because it is a shear hinge, of course you don't have these two, right? You don't have them. Because you are going to draw bending moment at point C, so you remove the constraint for bending moment. Again, the remaining is the horizontal one, which is free. So basically, you don't have, so if you redraw it, A, B, C is free. Now, apply a unit displacement at two sides of point C in this direction. What about A, B, C?
Stable.
Yes, because A and B are fixed, yes. So basically, this is a single element. You cannot move it unless Clement says there is a way to move this single element. It's a single element. It's stable. So you have to apply the unit slope at the right side That's it. So this is the interest. So this is unit slope. So this is 45. This is 45. And then if the length is L, then if this is L, this is L, this is L, this is L. Next question. We have a pin support at point A. We have a shear hinge at point B. The beam is sitting on a pin support at point C. Internal pin at point D. Fixed support at point E. Inference line for bending moment at point B. Okay, you have 30 seconds to challenge yourself. No, okay. Now, what do you think about, this is a shear hinge here. So, as usual, you draw moment, shear, normal force, and because it is shear hinge, we don't have these two constraints because we are going to remove the bending moment constraint. So forget about these two. So basically it's free. So you redraw it and now what would you do now? You have to apply this. Can you rotate AB? No? Why? This is AB. Can I rotate it? Yes. Because it's a pin. And I have to rotate it with a unit slope. What about BC? So this is point B. What about BC? This part is a bit, it may be challenging. Maybe for Clement, I don't know. Clement, what do you think about DE? Is it stable or not?
Yeah.
Yes? Okay. So do you agree there is no point on DE can move? So point D cannot move. Do you agree? So what about CD? Because you said point D cannot move. Point C is already fixed to the ground. So CD has to remain in this place. So CD is stable because it is attached to D. Right? What about BC? Remember, BCD is already a single element. It's a single element. So if CD cannot move, BC cannot move. They are attached together. So basically, this side is stable until B. Okay, so you just rotate this. 45. If this is L, this is L. And then the one that is stable means how much is the amount of inference line for this? 0. So those parts are stable, the amount of inference line is always 0. So it means you draw, in the exam, you just draw a line in this way. And you have to draw it. Okay? Okay. Now, a very typical question. It's a very typical question, so it means it is important. You have a pin support here, internal pin. So this is A, this is C, this is D. There is a point here, we call it B. From here to here is A, from here to here is B, L, L. Draw the inference line of shear at a point. So we are going to draw the inference line of shear force at point B. Basically, VB is the question. We are going to draw the inference line for internal shear force at point B. Internal shear force at point B. Okay, give it a try. I will solve. Okay. We have to do something at point B. As usual, you draw the force system. We have 6 components. And then we look at the constraints. We are going to draw the shear. So it means that this one is removed because it's shear. Remove the constraint, first step. So basically, the remaining is moment and normal force. So what is the proper internal joint? Shear hinge, yes. So we place a shear hinge here. I redraw it because it's important. D, C, okay. Next step, what is the next step? In the Mueller step said the first step is remove of the constraint, replace it with a proper support or internal joint. We have done it so far. And then apply a unit displacement. So what is the displacement here, Clement? Is it moment? Is it displacement, rotation? What?
Displacement for 1.
Displacement 1. In this direction, right?
Yeah.
Shear. But how to do that? This is a typical question. It is important. We have to go to this direction. So it means the left side moves down, the right side moves up. Okay. Oh, no. It must be like this. Moves down, moves up. So it's like this. But the problem is how much is this displacement? Let's call it x. So from here to here, I'll show it with x. From here to here is y. And you agree that both sides of the shear hinge must be parallel. So if this is alpha, the other side is alpha. The angle must be the same. Both sides of shear hinge must be parallel. And you already know that CD is stable. Okay. Stable. The problem is how much is x and how much is y. When I asked Clement, he said, I don't know, but he wanted to say something like this. X, he said unit. It means x plus y must be unit. This is what he said. Apply a unit displacement. It means x plus y together must be unit. So if you look at the triangles here, this triangle, you can write alpha is basically, alpha is the same. So tangent of alpha is the same. So opposite over adjacent. In the original question, this is actually A, this is B, in the original question. And in the original question, this is L, this is L. You have it here, right? So I can say x divided by A is equal to y divided by B. Y divided by B, because these are tangent of alpha. Tangent of alpha. Any question for this part? I'll just pause here. Selena, do you understand why x over A is equal to? Okay. So, from here, you find x and y in terms of A and B. X is A over L, y is B over L. It's a system of equation. The unknowns are x and y. A and B are just parameters. Solve this simple system of equation. You can find x and y. That's it. So we have x and y. So if it means if you have A and B and L, then you can find x and y. That's it. So maybe in the exam I'll give you the value for A. This is 10 feet, this is 12 feet. Then you can solve it. So this is an important typical question for internal shear force. And remember, the reason alpha and alpha are the same here is because these two lines are parallel, because two sides of the shear hinge must remain parallel, the same slope. Okay, next question. Is there any question in general? So there are a lot of details, as you can see. They are not difficult. You have to just pay attention. And you may forget some of them later. So my recommendation is just review this concept within next 24 hours. If you leave it for next week, you will forget some of the details. You don't believe me, you can try. Because we are human, we forget. So we have to review the content before it goes out of the mind. So maybe 24 hours. And then if you review it in 24 hours, the next time you are going to forget it would be around maybe 10 days. It means before you reach to 10 days, you have to review it again. That after 10 days, I mean, if you review it before 10 days, the next time it goes away from your mind maybe after 1 month. If you review it before 1 month, then maybe permanent. It's just about a matter of review. Next question. We have a fixed support at point A. We have a pin at point B. Pin support at point C. Roller at point D. Pin at point E. Draw inference line for shear force at point B. Shear force at point B. Again, these are the challenging questions I intentionally selected out of all the questions for you. So expect some challenge for this problem. Again, because we have time limitation, I'm going to start the solution. The question is asking for shear force at point B. So what is the proper replacement joint? Yes?
Free.
Yes, free. Because moment, shear force, normal force, shear force, it means you remove the constraint. And because we already have a pin in place, so we don't have moment. So basically it's just horizontal force. We don't have horizontal force in this beam, so we just leave it there. Now apply a unit displacement corresponding to this. And Clement, do you agree this is stable? So it doesn't move. So the only choice is the right side. So we just apply a unit displacement for the right side. Any question? We hold point B and lift it upward, 1 unit. So it means this is 1. This is 1. Because BCD is a single element, it totally rotates. It's a single element. What about DE? Parallel. So it means like this. This angle is equal to this angle is equal to this angle. So if this is L, 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 this is L, L, that's it.
If it's 1 though, wouldn't they be 1?
Oh, yes, 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 that's a good answer. This is 1, this is, so let me write it with yellow. This is 1, 1, 1. But the horizontal length is that. So let's discuss, for example, if I call it theta, then how much is tangent theta? 1 over 10. Yes? 1 over 10. So let's say you want to calculate theta. Tangent inverse 1 over L. Next question. it's an important question. We have a pin support here at point A. We have a pin support at point B. Internal pin at point C. Pin support at point D. Shear hinge at point E. So the length is just equal for all of the segments, L, 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 L. Draw the inference line. Draw influence line of shear force at left side of B. Left side of B. We solve it, and then you will understand why I am saying at the left side of. There is a reason for that. First step. So it means we have to do something with the left side of B. First step, it is about shear force. So it means you just cut somewhere very close to the B, but at the left side. So I just cut it, but it is left side of B. Because it is shear, then we remove the constraint. What is the proper replacement? Shear hinge. To save the time, I'm going to draw it here. So now you have the original figure, right? On your note. So I'm going to this is B. Braden, how much is this?
Undefined x, very infinitesimal.
Yes, very small. We show in mathematics, we show it with epsilon. Extremely small. Okay. Now, next step. Apply a unit displacement corresponded to the remove constraint. It's shear. So, do you agree that unit displacement must be in this way? Okay, we apply a unit displacement. What color should I use? What? Unit. Any questions so far? So from here to here is just unit. Forget about this small part because it's epsilon. What about BC? Of course, when BC has this small part. BC, what? Remains the same or what? There was a principle for two sides of shear hinge.
Has to be parallel.
Yes. So BC must be parallel to this pinch line because two sides of shear hinge. So BC is going to move in this way. And then CDE is a single element. So if you grab point C and lift it down, then CD is going to move in this way. Any question? Because CDE is a single element. It's a single element. CDE rotate together. And what about EF?
Stable.
Parallel.
Which one? Parallel or stable? I was expecting someone says stable, but it's not. EF can rotate about F. So why EF? Maybe race means parallel two sides, but EF is not stable. It can rotate about point F. So it must be parallel at two sides of the shear hinge. When we say parallel, it means these angles are the same. So of course you can find the dimensions of the inference line. So this is 45, this is 45, 45. That's it. And, oh, wait. I'm not sure if they are 45. They are parallel, but let's check if,
The shear, yeah.
yes. They are parallel, but let's check if they are, how much?
Be 1/L.
Yes, yeah. Similar to this. So, this is how much? How much is this, Braden?
L minus the input.
No, this one.
Oh, that's 1.
Unit, yes.
Yeah, sorry.
So it's 1. So this is theta. So theta is the one that we calculate here. Right? And how much is this angle? It's the same. So again, this is theta. And so this value here must be 1, because these two must be parallel at two sides of the shear hinge. And of course, when it is 1 and this is L, of course this one must be the same, because this is 1, this is L, this is L, so these two angles must be the same. Theta, theta. So theta is this one. Theta, tangent inverse 1/L. That's it. When it comes to the right side, so repeat the problem above for right side of B. So everything is the same, but right side. This is the last question for today. So for the right side, I draw it here. I draw the answer. A, B, we put a shear hinge at the right side. So this is where we put a shear hinge at the right side. And then apply a unit displacement. AB is stable. Do you agree? AB is stable. Apply a unit displacement. Maybe Clement doesn't like it, but I just move point B upward with unit displacement. It's a shear hinge. It can move. And it can break at point C, because point C is a hinge. So CDE is a single rigid element. So far everything is fine. What about EF?
Parallel.
Parallel, two sides of the shear hinge. So this is 1, this is 1. The dimensions are given, L, this is 1. This angle and this angle are the same, they are all the same. So if I call it theta, theta, theta. Theta is tangent inverse 1/L.